Hey everybody, this next video lesson is going to begin in chapter 11 in the textbook, and we're going to be talking about intermolecular forces here today. Now, a fair amount of this is review for most of you, but there might be some new tidbits of information, and we're going to go much deeper into the understanding of the differences in the intermolecular forces that you will be expected to know for the AP test. We are first going to begin with dispersion forces. Now, you might have learned that dispersion forces are the weakest of all the forces, but we're going to put that particular misconception to bed near the end of this video lesson. But what you do need to know about dispersion forces is that they are instantaneous dipoles that are the result of electron movement. Anything that has electrons, whether it be a polar molecule or a nonpolar molecule, will exhibit dispersion forces, which are attractions between two molecules. As long as molecules have electrons, and all of them do, they will have dispersion forces. Now, what do I mean by instantaneous dipole? What do I mean by that? Well, these are most often associated with nonpolar molecules, but polar molecules exhibit dispersion forces. We talked about that previously. But a nonpolar molecule does not have a dipole, but it may have an instantaneous dipole when all the electrons kind of pile onto one side of the molecule at any particular moment. Remember that electrons are dynamic particles that are always in motion, and due to just random electron movement, every once in a while, they may find themselves all on one side of a nonpolar molecule, and for a moment, there may be a slightly negative side of that molecule and a slightly positive side. Let me illustrate using this example of hydrogen. Now, hydrogen is a nonpolar molecule. It's quite small, and it's just sharing two electrons here. But every once in a while, the shared electrons might find themselves closer to one side of the hydrogen than the other. And this side of the hydrogen would have a partial negative side, and by contrast, then the other side would have a partial positive charge. Now, let the electrons continue to move, and at any given moment, maybe the electrons now are on this side. And now this side has a partial negative charge, and then the other side then has a partial positive charge. Now, if you get two molecules that are exhibiting these instantaneous dipoles at the same time and close enough to each other, they may begin to attract, and if the temperature is low enough, they may turn from a gas, in hydrogen's case, to a liquid. Or, even colder, might turn from a liquid into a solid. You're looking at an illustration from our textbook, and on the last slide, I talked about how just nonpolar molecules could exhibit instantaneous dipoles, but just simple atoms could as well. If it's got electrons and the electrons move, then it has instantaneous dipole, and as a result, could result in some dispersion forces. Now, take a look at two helium atoms here, and we've got helium atom A and helium atom B. Now, helium atom A has electrons kind of randomly dispersed throughout the electron cloud, and so does atom B. And because they're kind of equally dispersed, there is no instantaneous dipole. But in a moment of time, at some point later, maybe all the electrons from atom B find themselves on this left side. And as you can see now here on below in the polarization view, we've got a slightly negative side and a slightly positive side. Now, this atom A still has evenly distributed electrons, and so it is not exhibiting any dipole, but atom B has a dipole. Now, maybe you've got atom A and atom B both exhibiting the same sort of situation where all their electrons are piled onto one side, and we've got a slightly negative, slightly positive side for atom A and also for atom B. And for a moment in time, there might be a slight attraction. That is what we call an induced dipole or an instantaneous dipole due to just random electron movement. Now, there's a concept in the textbook which can be found on page 435, and it's a concept known as polarizability. Now, I'll read directly from the textbook. It says, the strength of the dispersion forces depends on the ease at which the charged distribution of the molecule can be distorted to induce an instantaneous dipole. The ease at which the charge distribution is distorted is called a molecule's polarizability. And so, in other words, polarizability is how easy a nonpolar molecule can become an instantaneous dipole. And that depends on how big the element is. The more electrons a molecule has, the more opportunity it has for electron movement, and the more likely there is an instantaneous dipole at any given moment over that molecule. And so polarizability is a way to explain how likely something is to become an induced dipole. The more polarizable a molecule, the stronger the dispersion forces. So to boil this all down into one statement, electrons increase generally as mass increases because mass increases as we add more atoms to a molecule, and so there are more electrons. And so the larger the mass of a molecule, the stronger the dispersion forces. This figure in the book helps explain kind of the concept of polarizability and how it affects boiling points of various substances. Now, as you can see, we've got in the second period fluorine and neon. Those are the halogen and noble gas, respectively, in that period. And as you can see, neon, which has an atomic weight of about 20, and fluorine, which has an atomic weight of about 40. Now, both of these are nonpolar molecules, but fluorine has a higher boiling point because it is more polarizable. It has a larger mass, it has more electrons, and those electrons can have a more likelihood of an induced dipole or an instantaneous dipole. And as a result, because of the higher mass, it has a higher boiling point. Now move down to the next period, and you can see that the noble gas once again has a lower boiling point than the halogen, which is directly to the left of it. But the halogen is diatomic and thus has more mass. More mass means more polarizable. More polarizable means stronger dispersion forces, and as a result, a higher boiling point. But let's compare a halogen like F2 to a halogen like Cl2. Both of these are nonpolar, but just like we said before, chlorine has a higher mass than fluorine, and as a result has a higher boiling point than fluorine because of its higher polarizability. Hopefully this graph helps show the connection between mass and polarizability and boiling points. And as a reminder, boiling points are a direct relationship between the strength of the intermolecular forces. So if something has a higher boiling point, it has stronger intermolecular forces. And mass certainly plays a role in determining the strength of the intermolecular forces, but also the shape of the molecule matters. And I'm going to show you a couple of examples here today of molecules that have the same identical mass, but the shape results in slightly different boiling points, and it must be because the shape affects the intermolecular forces differently. Now what we have on the left here is what is known as N-pentane, or just single carbon chain pentane, 5 carbons and 12 hydrogens. Now because it has all the carbons in a straight line, there's more surface area, and the larger surface area enhances the intermolecular contact and increases the dispersion forces. If you take something like neopentane, which has the same chemical formula, it's C5H12, but you can see that the carbons aren't in a chain, but they're rather all kind of clumped up in the middle, and the hydrogens are kind of coming off of that center clump of carbon. And this spherical molecule is much tighter and has a much smaller surface area, so there's less contact between two molecules of the same type. And if there's less surface area to come in contact with, then that diminishes or lowers the intermolecular forces. And as a result, you see a slight drop in the boiling point of something that, even though they have the exact same formula, the one on the right has less surface area, and so it has a slightly lower dispersion forces and a lower boiling point as a result. So shape certainly plays a role in determining the amount of dispersion forces that something may exhibit, but certainly the mass has a greater effect than the shape. Now we're going to talk about dipole-dipole intermolecular forces. And dipole-dipole intermolecular forces only happen between polar molecules because polar molecules are the only ones that have dipoles. If you take a look at this molecule, you've got CH3CN, and we've got this molecule with a nitrogen here on the end. Now this nitrogen comes equipped with 2 electrons that kind of hang out at the tip of this molecule, which means that the molecule is polar. It's got a partial negative side over here and then the partial positive side on the first carbon here at the bottom. When the temperature is low enough, this molecule can line up where its negative side is closely attracted to the positive side of a neighboring molecule, and that is the dipole-dipole intermolecular force. It's the attraction between dipole of one molecule and the dipole of another. Now, if you warm up the temperature a little bit, those molecules start to move around and wiggle, and maybe they break some of their intermolecular forces. Maybe they spin, rotate, and so you get maybe a situation in a liquid state where the negative side of one intermolecular molecule is repelling another molecule because their negative sides are close to each other. and not their opposite sides. And sometimes you get some repulsive forces, which we have in blue here. But we still have some attractive forces between the molecules, which keep them as a liquid state. Now, in a gas state of matter, if you heat up the temperature large enough, you have enough energy to break all of these intermolecular forces from one another, and then the molecule begins to vaporize. But this picture is supposed to show you the difference between the intermolecular forces of a solid compared to the intermolecular forces of a liquid. Now, previously we talked about how the dispersion forces are variable depending on the amount of polarizability of a molecule, and polarizability increases with mass. And so we can also consider the difference in polarity between dipole-dipole molecules. And I've got 4 molecules here all lined up, and they're all very similar in molecular weight. And so in other words, they are all equally polarizable and have the same dispersion forces. But as you can see, the boiling points increase moving to the right because the measure of the dipole-dipole interactions increase moving to the right. Now this first one is your nonpolar molecule. This is just propane. That's CH3, CH2, CH3, kind of all in a straight line. But this next one has an oxygen where previously there was a carbon. And so you can see that the measure of dipole-dipole interaction goes from 0.1 up to 1.3. And that's what this metric is measuring, is the amount of dipole interaction. So 1.3 is bigger than 0.1, as you would expect, because it has an oxygen now with a pair or two of electrons that are hanging out on this oxygen. Now, if we maybe take that oxygen and instead of making it the center of the chain, we stick it on the end, and all of a sudden the pair of electrons becomes more to the outside, and the dipole-dipole ability increases from 1.3 to 1.7, and the boiling point increases from 248 to 294. And finally, if you put a nitrogen in the spot of the oxygen, maybe out here on the end, and you've got yourself a more polar molecule even yet. And the polarity increases to 3.9, and the boiling point increases proportionally. So increasing in polarity, increasing strength of dipole-dipole forces shows an increase in boiling point. Now let's talk about hydrogen bonding. Hydrogen bonding is something that you were introduced to in a previous chemistry class, possibly, but if you weren't, I'm going to describe it right now. Hydrogen bonding is a special case of dipole-dipole interaction in which hydrogen is bonded to either oxygen, nitrogen, or fluorine, and when hydrogen is bonded to any one of these, the difference in electronegativity between hydrogen and the element that it's bonded to is so strong that it creates a very large dipole. And so that dipole ability that we talked about on the last slide is very large, and as a result, that increased dipole ability causes an increased attraction to a neighboring molecule, and as a result, you get high boiling points of substances that exhibit hydrogen bonding. Let's take, for example, 2 molecules that look very similar, but one exhibits hydrogen bonding and one doesn't. The first one is NH3. Now, NH3 has nitrogen in the middle, and it's bonded to 3 separate hydrogens. It's a polar molecule because it's trigonal pyramidal, and it exhibits hydrogen bonding because it has hydrogens bonded to the nitrogen in the center. And that dipole difference between hydrogen and nitrogen when it comes to the bond dipoles is so large that it creates a very, very large dipole-dipole intermolecular force with something around it. Now, compare that to pH3, where you've got P in the middle with H's coming off, and you still got a pair of electrons on the P. And it's also a trigonal pyramidal molecule. And because it's trigonal pyramidal, it's polar. But the difference in electronegativity between the phosphorus and the hydrogen is not very large compared to the difference in electronegativity between the hydrogen and the nitrogen on its molecule that it's being compared to. The difference in electronegativity, in fact, is so small that it's considered essentially nonpolar, the bond anyway. It's 2.6 for phosphorus and 2.2 for hydrogen, or a difference of 0.4. So it is a polar molecule, but it does not exhibit hydrogen bonding, and as a result, it will have a lower boiling point than its buddy NH3, which would have a significantly higher boiling point. Hydrogen bonding is the reason that water creates these very strong and rigid hexagonal crystals when it freezes. And it's the core of every snowflake. Every snowflake starts out as a 6-sided crystal, and which is why every snowflake has 6 arms. As you may know, when water freezes and creates these 6-sided hexagons, it actually expands when it freezes, which makes it less dense in its solid state than in its liquid state. and as a result, it will float on its liquid self. Now, this particular characteristic of water has many, many implications that are hugely advantageous for us as humans to survive and for us to live on our planet, which is 70% water. Because if the solid state sunk down into its liquid form, we would not have ice on top of lakes. We would not be able to go skating. We would not be able to go ice fishing. We would not have any life that exists in the oceans because they would freeze from bottom up rather than from top down. And if they freeze from bottom up, everything would die. And life, as we know it, would not have existed because scientists have hypothesized for many, many, many years that life began in the oceans and moved out onto land after many, many thousands of years. So if water didn't do this, then life would not exist and we would not be here today. The last intermolecular force that we are going to be talking about today is called the ion-dipole intermolecular force. And that's not really an intermolecular force, but rather an interparticle force. But we put it in as an intermolecular force anyway. What happens here is that a dipole, or a polar molecule, has an attraction to an ion that has been dissolved in it. And so when you have something like water, which is your classic example of a polar molecule, which has a positive end and a negative end, and you dissolve ions into it, the positive ions and the negative ions are going to behave slightly differently with the water, because the positive ion is going to align itself with the negative side of the water molecule. And as a result, you get water surrounding the positive ion with all of its negative sides, and this is what is known as a hydration sphere. Now, the other ion is a negative ion, and the opposite would be true, where the positive side of the water would surround the negative ion in what is known as hydration sphere, but the orientation of the water molecules compared to the negative ion is obviously different than it is with the positive ion. But this attraction between the positive side of the dipole molecule and the negative ion is what is known as an ion-dipole intermolecular force. Now let's talk about the strength of intermolecular forces. You've probably been told in a previous science class that the dispersion forces are some of the weakest intermolecular forces, and dipole-dipole are always stronger, and hydrogen is an even stronger form of dipole-dipole interaction. But that is not entirely true. In fact, you can't really compare dispersion forces and dipole-dipole forces because there are lots of counterexamples in which the dispersion forces are actually stronger than a molecule's dipole-dipole interactions. You can compare the strengths of dispersion forces compared to each other based on polarizability. And you can compare the strength of dipole-dipole interactions with other polar molecules' dipole-dipole interactions, but you cannot compare them to each other unless you know specific information about the two molecules that you're trying to look at. And the best indicator of which substance has the stronger intermolecular forces overall would be boiling point, because the reason boiling point exists is due to the intermolecular attractions between the molecules. And if something has stronger intermolecular attractions, then it's going to have a higher boiling point. And if something has weaker intermolecular attractions, then it's going to have a lesser boiling point. Now, I talked to you at great length about how you can compare dispersion forces using polarizability, but you might be asking yourself how you compare dipole-dipole forces. Well, you simply need to look at how many times they attract another molecule of the similar type. So if you, say, for example, have a molecule that has one oxygen at the end of it, and it's being attracted to another molecule with an oxygen at the end of it, well, that is forming one dipole-dipole interaction. But let's say you have a molecule that has two oxygens on the end of it, and it's going to be attracted to another molecule that has two oxygens on the end of it. And then you can safely assume that because it has double the oxygens, that has double the strength, or at least increased strength, of intermolecular attractions with the molecules next to it. So in summary, it's not possible to compare dispersion forces to dipole-dipole intermolecular forces. You can compare dispersion forces to each other based on polarizability. You compare dipole-dipole forces to each other compared to how many times those dipoles interact with other dipoles. And the best way to compare dispersion forces to dipole-dipole forces would be to utilize the boiling point data if you have it. Otherwise, you will be unable to compare them. Well, that takes care of this video lesson on intermolecular forces. Thanks for listening.